Hey devs, welcome to episode 1 of this brand new Unity series where we build a complete 2D RPG game from scratch using Unity 2D. This series is perfect for beginners and intermediate Unity developers who want to sharpen their skills while creating something fun and meaningful. A full RPG game from the ground up. And good news, every tutorial comes with free downloadable assets, sprites, animations, and prefabs so you can follow along easily. Each chapter builds on the last, so if you stick with me, you'll not only learn Unity, you'll master it. Let's start by creating a new Unity project. Open Unity Hub, hit New Project, choose 2D and name it something like RPG Adventure. Once we're inside Unity, let's organize our project to keep things clean. Create the following folders: Scripts, Scenes, Sprites, Animations, Prefabs, UI. This will help us manage everything as the project grows. Now let's import our player sprites. I've added the download link in the comments section, so make sure to grab it and drag it into your project's Sprites folder. If you click on the player sprite in the project window, you'll see in the inspector that we have the entire sprite sheet. Make sure that the sprite mode is set to multiple. This tells Unity we're working with a sprite sheet that contains multiple frames. Now, if you click the small arrow next to the sprite in the project window, you'll see that all the player sprites have already been sliced and are ready to use. Idle, walking, up, down, everything's in place. Let's drag one of the player sprites into the scene view to test it. You'll probably notice that it looks a little blurry. That's because of Unity's default filter settings. To fix that, select the main player sprite sheet in the project window. Then in the inspector, scroll down to Filter Mode and set it to Point, no filter. Click Apply. Now the sprite is sharp and pixel perfect, exactly how a retro RPG should look. If your sprite colors still look off, scroll a bit further and change the format to RGBA 32-bit, then hit Apply again. That should clean up any weird coloration or transparency issues. Awesome! Now we've got a clean, crisp pixel art character ready to animate. Next, we'll create animations for idle and walking in 4 directions, and hook it all up with Unity's Animator system. Now that we've got our sprite looking nice and sharp, let's start preparing it for gameplay by adding some physics components. First of all, select your player game object in the hierarchy. Go to the inspector, click Add Component, and choose Capsule Collider 2D. Now adjust the collider size and offset so it fits the player's body properly, especially around the torso and legs. You want it to match the actual movement area, not the entire sprite size. Next, add a rigid body 2D component to the same player object. By default, Unity applies gravity to rigid body objects. But since this is a top-down RPG, we don't want our player falling through the floor. So, set the gravity scale to 0. One last tweak. Go to the constraint section inside the rigid body 2D component. Under freeze rotation, check the box for Z-axis. That prevents the player from accidentally spinning when colliding with objects. And that's it. Your player now has a clean capsule collider, no gravity, and locked rotation. Everything is ready for smooth and controlled movement in a top-down world. Now, let's add some movement logic to our player. Inside the Scripts folder, right-click and create a new C# script. Name it Player Movement with no spaces. Then double-click to open it in your code editor. I'm using Visual Studio, but you can use whatever you prefer. Alright, first let's get rid of the start method. We're not using it right now, so we can keep the code clean. At the top of the class, let's define a movement speed and set it to 5 feet by default. Then, let's create a reference to the rigid body 2D component so we can apply movement to our player. Let's go over what we just did. In the fixed update method, which is made for physics updates, we read player input from the horizontal and vertical axes, so that works with arrow keys by default. Then we apply movement using rb.velocity. Now, let's save the script and go back to Unity. Select your player game object, then drag and drop the player movement script into the inspector. You'll see a new field appear for the rigid body 2D. Just drag the player's own rigid body 2D component into that slot to assign it. Now hit play. You can now move your character using the keyboard. It's a simple system, but it gives us full control over the player's direction and speed. And it'll be the foundation for animations and collision next. Now, in this part, we're going to animate our player so that they're not just sliding around, but actually walking. Go to the top menu, click on Window, then Animation, to open the Animation tab. Before we begin, let's give our player a proper name so things stay clean. I'll just rename mine to Player if you haven't already. Now, select your player game object, then in the Animation tab, click Create. Let's save the new animation in the Animations folder and name it something like Player Walk Down. We'll start with the down walking animation. Now the fun part, animating. Head over to your Sprites folder. Select all the frames for the walking down animation. You can hold Shift and click to select them all. Then just drag and drop them into the timeline in the animation window. If you hit play right now, the animation works, but it's way too fast. To fix that, click and drag the right edge of the timeline keyframes to space them out a bit. This will slow down the animation. And here's a cool tip. To make the animation loop more smoothly, just copy the first frame and paste it at the end of the timeline. That way, it ends where it began. No snapping or popping. Now hit play again, and you'll see that the walking animation looks natural and fluid. And that's it. We've successfully created our first animation clip. Our player is no longer just floating. They now have a walking animation ready to be connected with movement logic and direction handling. In the next part, we'll dive into Unity's Animator controller and hook up all directions, up, down, left, right, based on keyboard input. Don't forget, all the sprite sheets used in this animation are available for free download in the comments section below. Now, let's add an idle animation for the player, following the same exact steps we used for the walking animation. But before we start, let's make sure we bring in the second player sprite sheet that includes the idle animations. Just drag the new file into the sprites folder. Make sure it's sliced like the first one. Sprite mode set to multiple, then slice it using the sprite editor if it's not sliced already. Now, select the player game object again and go back to the animation window. At the top left, click on the drop-down where it says the current animation name and select Create New Clip. Let's name this one Player Jar Idle Down and save it inside the Animations folder. Just like before, select the idle animation frames from the new sprite sheet. Shift plus click to select them all. Then drag and drop them into the timeline. Again, it's a little fast by default, so stretch the frames in the timeline by dragging the right side to slow down the animation. And for a smooth loop, just copy the first frame and paste it at the end. That gives it a nice natural idle cycle. Now hit play, and you'll see that the idle animation looks pretty good, smooth and subtle, just like in a classic top-down RPG. Awesome! You now have both walking and idle animations ready to go. In the next part, we'll dive into Unity's Animator controller and set up transitions between idle and walking depending on movement input. This is where your character will really come to life, changing animations based on direction and speed. Now that we've got the basics set up, movement and animations, let's connect everything using Unity's Animator controller. Head to the window menu, go to Animation, Animator. Now, with the player selected, you'll see that the walk animation is currently set as the default animation state. Let's fix that. Before we start flipping the sprite to face left and right, we need to actually create a sidewalk animation for the player. First, select your player game object in the hierarchy. Then head over to the Animation tab, the same one we used for the idle and downwalk animations. In the animation window, click the drop-down next to the clip name and choose Create New Clip. Name this one Player Walk Side and save it in the Animations folder. Now head to your Sprites folder and select the frames for the sidewalking animation. These usually show the player facing sideways. Shift+click to select them all, then drag and drop the frames into the timeline in the animation window. As always, if it looks too fast, stretch the animation by dragging the timeline keyframes outward. And don't forget to copy the first frame and add it at the end. That creates a nice smooth looping animation. Now we've got a proper sidewalking animation, perfect for use with horizontal input and sprite flipping. Now that we've created separate animations for walking in different directions, it's time to clean up our animator and replace everything with a blend tree, a much better way to handle 2D directional movement. Open the Animator window and you'll see the entry and exit nodes, along with your old idle and walk states. Go ahead and delete all the animation states so we can start fresh. Don't worry about the entry and exit points. We won't be using them in this setup. Now right-click anywhere in the Animator workspace and choose Create State from New Blend Tree. Let's rename it to something clear, like Player Tree, and then double-click on it to open the Blend Tree editor. By default, the blend tree uses a parameter called blend, but for our top-down player, we need to use two input parameters, one for X and one for Y movement. Click the Parameters tab in the Animator window. Rename the default parameter blend to Zinput. Click the plus icon and add a new float. Name it Yinput. These values will later come from our movement script. In the inspector, with the blend tree selected, change the blend type to 2D Simple Directional. Then make sure that the two parameters used are Shinput and Yinput. Now we'll add 4 motion fields, one for each movement direction, right, up, left, and down. Click plus, add motion field 4 times. Assign the appropriate animation clips for each direction. Our first motion will facing the right positive one for the X and 0 for the Y. Second one is 0, and 1/3 one is -1 and 0, and the last one is 0 and -1. For the walk left animation, we'll use the same walk side clip, but later we'll flip the sprite using sprite_renderer.flipx. Now we've got a proper 2D blend tree that will automatically transition between different walk animations based on input direction. Next, we'll go back to our movement script and hook up the values for Zinput and Yinput and add sprite flipping when going left. Now that we've built our blend tree with X input and Y input, let's update our movement script to actually send those values to the animator. Open the player movement script. At the top of the class, let's add a reference to our animator component. Now inside fixed update, right after we capture movement, let's pass the input values to the animator. These values will now drive our blend tree and control which animation gets played depending on the direction. Back in Unity, don't forget to drag the animator component into the animator field on your player movement script in the inspector. Hit play, and now you'll see that your player transitions smoothly between up, down, left, and right walk animations, all based on your keyboard input. One last touch. If you're using the same sprite for left and right movement, you can flip it horizontally when going left. Now, to make our player actually face the right direction, we need to flip the sprite when moving left. All we have to do is add a reference to the sprite renderer and flip it based on horizontal input. Now inside the fixed update method, right after setting velocity and animator parameters, add this logic. This will flip the player's sprite when moving left and return it to normal when moving right. Make sure your player game object has a sprite render rand. Drag it manually into the scripts field in the inspector. Hit play and try moving left and right. You'll see the sprite flip smoothly based on direction, just like you'd expect in a polished 2D RPG. And that's it. We now have movement, animation transitions, a 2D blend tree, and directional flipping all working together. Hey everyone! Welcome back to the third episode of our 2D RPG series in Unity. In this video, we're diving into Unity's built-in Tilemap system, which is super useful for building game environments like towns, dungeons, and forests. First, let's import the tile sprites we'll use. I'm using this tile sheet. Just drag it into your sprites folder in Unity. Now we need to set it up properly. Select the sprite asset. Set sprite mode to multiple. Make sure pixels per unit is 32, set filter mode to point, no filter. And for format, choose RGBA 32-bit. Once that's done, click on Sprite Editor. In the Sprite Editor, we're going to slice the tile palette. Change the slicing type from automatic to grid. By cell size, set the cell size to 32 by 32 pixels. Then hit Slice and click Apply. We're now ready to use these tiles in our Tilemap system. Now that our tile sprites are sliced and ready, let's start tiling. First, we need to create our Tilemap object. This will serve as our ground layer. Right-click in the hierarchy. Go to 2D Object, Tilemap, Rectangular. This creates a grid parent with a child. Rename the tilemap to something like ground. Before we start placing tiles, we need to create a tile palette. Go to Window, 2D, Tile Palette. Dock the Tile Palette window inside the inspector or wherever it's comfortable for you. Click Create New Palette and name it Grass Tiles. Then click Create. It will now ask where to save the tile assets. Let's make a new folder inside our Sprites folder and call it Grass Tiles. Now we have an empty palette. Time to populate it. Drag the sliced tile sprite sheet into the palette window. Unity will generate individual tiles. Save them in the grass tiles folder you just created. Now select the palette and you'll see your tiles appear. Finally, make sure the grid visibility is toggled on so you can align tiles perfectly when painting, especially since we're using a 32 pixel tile size. Alright, we're all set to start building our game world. Let's paint some terrain. Now it's starting to feel a bit like working in Photoshop. Just select any tile from the palette and start painting your ground layer directly in the scene view. You can paint one tile at a time, use the bucket tool to quickly fill large areas, or even use the eraser tool to remove unwanted tiles. Once your scene starts looking good, go ahead and hit the play button to test things out. But wait, you'll notice something odd. Our grass tiles are rendering on top of the player. That's a layering issue. To fix it, select the ground tile map in the hierarchy. In the inspector, set its order in layer to -1. By default, the player sprite is being rendered at layer 0, so setting the ground to -1 makes sure it stays behind the player. Hit play again, and the player is now correctly rendered in front of the ground. Let's go ahead and paint a bit more terrain to expand the map and make it feel like a real game world. Alright, now let's add a bit of variety to our map. We're going to place a small hill. I've already imported a tile sheet that contains some hill tiles. Inside our grid, let's create a new rectangular tile map and name it Hills. Now just select the hill tiles from the palette and start painting your hills into the scene. When we hit play, it looks great. The hill gives the world more depth and variation. But there's a small problem. Our player can walk right over the hill, as if it's just part of the ground. Let's fix that by adding collision to the hill layer. Select the Hills tile map. In the inspector, click Add Component. Choose Tile Map. Collider 2D. Once added, Unity will automatically generate colliders based on the shape of the tiles. Zoom in and you'll see a green outline. This represents the collider boundaries. And just like that, your player can no longer walk through the hills. You can fine-tune the collision later using a composite collider for smoother edges, or even customize collisions tile by tile using a custom tile asset. Alright, now let's make our map feel more alive by adding some trees, rocks, and decorative details. To do that, we'll add a new tile map specifically for decorations. Inside our grid, right-click and go to 2D Object, Tile Map, Rectangular rename this new tile map to Decoration. Open up your tile palette and select some tree and rock tiles. Now just start painting them into the scene. Place trees near the edges of the map, rocks near paths, maybe even a few shrubs to break up empty areas. It's starting to look much more like a real game world now. Hey everyone! In this video, we're going to fix some of the layering issues we've been dealing with. Right now, when our player walks around the map, objects like trees or rocks don't always behave realistically. Sometimes he walks on top of them or disappears behind them in weird ways. So let's fix that and make our world feel more believable. Let's take a look at our current setup. We have 3 tile map layers: ground, hills, and decoration. The ground is set to order in layer equals -1. The player is set to order in layer equals 4. The decoration layer is at order equals 0. That setup is a good start, but we need more control. So in this video, we're going to create 4 new tile map layers, each with a specific purpose: collision behind player. This layer collides with the player, but is rendered behind him. Great for things like short walls or fences the player can walk in front of. Set order in layer equal to 2 collision above player. This one also collides with the player, but is rendered in front of him. Perfect for things like cliffs, big tree trunks, or upper bridges. Set order in layer equal to 5, non-collision high. No collision, the player can walk through it, but it's rendered above the player. Ideal for treetops, canopies, or vines. Set order in layer equals 6 or higher. Non-collision low. Also no collision, but it's rendered behind the player. Useful for roads, dirt paths. Grass details. Set order in layer equal to -2 or -3. With this structure, our player can now walk. Behind trees, but only the top part hides him. Around rocks that block movement. On top of roads that don't interfere with collision. This makes everything feel much more natural, like classic Zelda-style movement. All right, now let's refine our tile map setup to fix a classic issue. Our hill or elevated objects are appearing completely above the player, even the parts that should be behind him. What we want is to split those hill tiles, so the bottom part is rendered behind the player, and the top part is rendered in front, while still keeping the collision accurate. So here's what we're going to do. First, head back to the sprite editor. We need to ensure that each block of the hill is sliced individually so we can separate the top and bottom tiles. If your hill tiles were sliced as one big tile, that won't work. Change the slice type to grid by cell size and reslice it so every block is isolated. Now, in the hierarchy, rename your current hill tile map to collision high. Then right-click on the grid and create a new tile map, rectangular, and name it collision low. In the inspector, set collision high to order in layer equals 5 and set collision low to order in layer equals 0. Now here's the trick. Select the eraser tool. Go to the collision high layer. Erase the bottom parts of the hill tiles, then switch to the collision low layer and place those same bottom tiles back in, just the base parts. When we hit play, you'll now see that the bottom of the hill is rendered behind the player. The top of the hill is rendered in front of him. This gives your environment a much more realistic sense of depth without breaking any collisions. Now let's apply the same technique we used for the hills to our trees. The goal here is to split the tree tiles into top and bottom parts, so that the player can walk in front of the trunk but appear behind the top leaves. First, make sure your tree sprite is properly sliced in the sprite editor. Then go back to the hierarchy, and just like before, now let's delete all the tree from the decoration layer and let's add a trunk on top of the collision low layer. Alright, before we move forward, there's a small change we need to make. Let's go back and rename our decoration layer to non-collision high, since it contains things like treetops or other objects the player should walk behind. Now, let's actually place some top parts of trees, the leafy canopies. These go on the non-collision high layer. Set their order in layer to 10 to make sure they render well above the player. This gives us that classic RPG effect where the player can walk under trees, but only the leaves cover him, not the trunk. Next, let's create a new tile map just for the tree trunks. Right-click on the grid. Go to 2D Object, Tilemap, Rectangular. Name it Tree Trunk, set its order in layer to 0. Now let's paint some tree trunks into the scene using sliced tiles. To make sure the player can't walk through them, go to the inspector and add a Tilemap Collider 2D. Then we need to adjust the collider offset slightly so it matches only the upper body of the player, giving the illusion that their legs are behind the tree, but their head is in front. You can tweak this by editing the collider's Y offset or shape in the Tilemap Collider component or by using a custom physics shape in the sprite editor. Now hit play and you'll see the player is correctly affected by the tree trunk collider while still appearing under the top part of the tree. This kind of layering makes your world feel more dynamic and adds that nice classic RPG polish. Let's go ahead and finish setting up our system by splitting it properly across the correct layers. Start by selecting the collision high tile map. Use the eraser tool, delete the top part of the trees, then switch over to the non-collision high layer and paint them back in the same position. Now when we hit play, this creates a beautiful depth effect and really brings the map to life. Next, let's add a layer for roads, paths, or extra map decorations that are purely visual. Right-click on the grid, create a new tile map, rectangular, name it non-collision. Low set its order in layer to 0 so it renders behind the player. Here you can add things like dirt roads, shadows, cracks, puddles, and other small map details. Since this layer is just for visuals, we don't need to add any colliders. The player can walk right over them freely. And that's it for this episode. We now have a fully layered and realistic map where the player can walk behind trees, around obstacles, and interact with the world in a much more immersive way. If you found this helpful, don't forget to smash that like button, subscribe, and turn on the bell so you don't miss the next episode, where we'll bring our world to life with animations and interactions. Thanks for watching, and keep building your dream RPG, one tile at a time. Hey everyone, welcome back to the series. In this video, we're going to take your RPG world one step further by adding a sense of verticality. That means giving the player the ability to climb up hills and walk inside areas that feel raised, just like in classic RPGs. If you've been following along, you should already have a player that can walk around a beautiful map with multiple tile map layers, proper sorting and collision setup. Now here's the challenge. Right now, when the player walks into a hill, he still renders underneath it, like it's a wall. What we want is this. When the player climbs into a hill, he should be rendered on top of the base of that hill, as if he's walking up and inside it. This small trick makes your world feel a lot more dynamic, and it opens the door for future features like stairs, ledges, bridges, and multi-level exploration. Now, let's add a bit of logic to our hills to give them real gameplay functionality. We want the player to be able to walk into hills, not just bump into them. So when the player enters a hill area, the collider should be disabled, allowing them to pass through. Let's start by creating a new C# script. Right-click in the Scripts folder, choose Create a C# script. Name it Hill Entry. Once that's done, double-click to open it in Visual Studio or your code editor. Inside the script, we don't need Start or Update, so go ahead and delete them to clean things up. The main idea behind this script is to disable the Hills collider when the player walks into a trigger zone. Since we might have multiple hills in the scene, we'll make this script flexible by referencing an array of 2D colliders. In this script, we're using onTriggerEnter2D to detect when the player enters the hill area. If the object colliding has the tag player, we loop through all the referenced hill colliders and disable them. This way, we can support multiple hills and keep everything modular and reusable. Alright, now let's go back to Unity and add a visual way for the player to climb into the hill. We're going to add some stairs into the scene, which will act as the entry point to the hill area. First, let's import our stairs sprite. Drag it into the sprites folder. Just like we did before, select the sprite and go to the inspector. Set the filter mode to point, no filter. And finally, apply the correct compression format if needed. Once that's done, go ahead and drag the stairs into your scene and place it right in front of the hill entry point. Now, let's go back to our non-collision low layer and apply the logic we just created. We're going to attach the hill entry script to the stairs or any object that represents the hill entrance. You'll see a field now to assign the hill colliders array. Let's go ahead and select the collision high tile maps from the hierarchy and drag them into the array in the inspector. This connects the script to the hill areas we want to deactivate. Now we need to add a box collider 2D to this game object to act as our trigger area. Click Add Component. Box Collider 2D, make sure to check is Trigger. Then use the resize handles in the scene view to adjust the collider so that it fits precisely over the stairs. This collider is what the player will walk into to trigger the hill entry logic. Once the player touches it, the script will disable the hill colliders, allowing them to move into the hill area naturally. Let's jump back into our hill entry script and finish the logic. The idea here is, when the player enters the trigger zone, we'll loop through all the hill colliders and disable each one. And at the same time, we'll tell Unity to render the player on top of the hill. But first, we need to make sure that the object colliding is actually the player. Let's add an if check to verify the tag. Now inside that check, we'll add a for each loop to go through all the colliders in the array. Before testing it out in Unity, here are a few things to double check. Make sure your player game object has the tag Player. Make sure the box collider 2D on your trigger zone is set to isTrigger equals true, and confirm that the hill colliders you referenced are correctly set in the inspector. Now when you hit play, as soon as the player walks up the stairs and enters the hill trigger, the hill becomes passable and the player is rendered on top of it, simulating elevation. Alright, now we've got a small issue. Our player can now enter the hill, but there's nothing stopping them from walking out the wrong way. For example, walking out the top or sides of the hill. We need to add a boundary system to make sure the player can only enter and exit the hill through specific paths like stairs. Here's how we fix it. Let's go back to our grid object, right-click and choose 2D object, Tilemap. Rectangular name, this one, Hill Boundary. Now go to your tile palette and select a solid tile, a rock, cliff piece, or even an invisible boundary tile if you have one. Paint the edges or walls of the hill, anywhere the player shouldn't be able to walk through. With the hill boundary tile map selected, go to the Inspector Click Add component and select Tilemap Collider 2D. This will make the painted tiles solid. You can make the boundary tiles invisible by assigning a transparent tile or material, so players don't see them, but they still work for collision. Now hit play and test. You'll see that. The player can enter the hill through the stairs, but can't exit from the sides or back, thanks to the new collision boundaries. I hope you're having as much fun following this series as I had preparing it for you. If you're enjoying the journey so far, don't forget to smash that like button and subscribe to the channel. It really helps me keep the tutorials coming. Thanks for watching, and I'll see you in the next episode. Hey there, I hope you're doing well and still having fun following this Unity series. I'm definitely having fun making it for you. If you haven't already, make sure to subscribe to get more Unity RPG content and keep building with us every day. Now that we've set up our hill entry trigger and added boundaries to control where the player can go, we need to take care of one last detail. When the player leaves the hill, we want to re-enable the hill colliders so they can't walk back through the sides or glitch out the map. We need to add a copy of our hill collider, and this one is going to be boundary colliders. We can now duplicate this for each loop. And now for each collider 2D, let's call it boundary. We need to enable the boundary. Before we hit play and test everything, there's one last step we need to take. In Unity, we want to make sure that the hill boundary colliders are not active by default, because we only want them to be enabled when the player exits the hill. So here's what you need to do. In the hierarchy, select your hill boundary tilemap. In the inspector, scroll down to the Tilemap Collider 2D component and simply uncheck the checkbox to disable the collider at the start of the game. This means the player can walk into the hill as intended, and then, when they exit, our script will reactivate the colliders, blocking the sides and back of the hill again. Alright, let's test it out. When we hit the play button and walk up the hill, everything works great. The player can enter the hill, and the boundary keeps us from falling off the back or sides. But there's a small issue. When the player leaves the hill, the boundary stays active, which means they can't go back in through the same entrance. So let's jump back into our hill entry script and fix this little problem. We can add the fix inside the same script, but let's take a moment to clean up our code using a best practice called separation of concerns. Right now, we can do both the hill entry and the exit logic inside the same script. While that works, it can quickly become messy, especially as your game grows. So instead, we're going to split the responsibilities by creating a new script just for exiting hills. This keeps each script focused on a single task, which makes things easier to maintain, debug, and expand later. Let's go ahead and create a new script. Right-click in your Scripts folder, choose Create, C#, script, name it, Hill Exit. Now open it in Visual Studio. Just like before, delete the Start and Update methods. We won't be needing those. Next, we'll copy the logic that was in onTriggerExit 2D from our Hill Entry script and move it here inside the new Hill Exit script. Let's also make a couple of naming tweaks to fit our new script. This new script now takes care of everything that should happen when the player exits the hill. It re-enables the hill colliders, turns off the boundaries, and resets the player's sorting order. Now you just need to assign this script to a separate exit trigger zone in your scene, and you're good to go. Alright, now that we've created our hill exit script, let's go back into Unity and set up a proper exit trigger zone for our hill. This is what the player will walk through to exit the hill, which will reset the collider and sorting state. First, in the hierarchy, right-click on your scene and select Create Empty Rename this game object to Exit. With Exit selected, go to the inspector. Click Add Component Box Collider 2D. Now resize the collider to fit snugly around the bottom part of your stairs. This is where the player will be leaving the hill. Make sure to check the Is Trigger box. This is super important for detecting player movement through the zone. Finally, click Add Component again and attach the Hill Exit script. Then, in the inspector, drag and assign your hill colliders to the hill colliders array, your hill boundary tile map to the boundary colliders array, and that's it. Now, when the player walks through the bottom of the stairs, everything resets properly. The hill colliders come back, the boundary is disabled, and the player's rendering order goes back to normal. Our entry and exit system is now clean, modular, and working like a charm. Alright, let's hit that play button and jump right into it. If you're enjoying this Unity RPG series and building along with me, make sure to subscribe to the channel and smash that like button. It really helps the channel grow, and you won't miss the next episode where we keep leveling up our game. All right, now that we've got our player moving around the map, it's time to add a touch of realism to our game by making the camera follow the player. Without camera movement, our scene feels static and limited. But with a smooth follow camera, we'll bring our world to life. First, let's install Cinemachine, Unity's built-in camera system that gives us powerful tools without needing to write a single line of code. In Unity, go to the top menu and select Window Package Manager. In the Package Manager window, set the drop-down to Unity Registry Search for Cinemachine. Click Install. This might take a few seconds, and once it's done, we'll have access to Cinemachine features. Next, we'll create a Cinemachine camera. Assign the player as the target and tweak the settings to get that smooth follow effect. Let's set it up. Now let's click the play button, and there we go. You'll see that the camera is now following the player as they move across the map. This immediately makes the game feel more alive and dynamic. No more being stuck in one spot or cutting off parts of your world. And the best part, we didn't have to write a single line of code. Cinemachine takes care of it for us. And if you're finding this tutorial helpful so far, make sure to smash that like button and subscribe to the channel. It really helps me keep this series going, and you'll get notified when the next RPG feature drops. So far in our RPG series, we've got our player moving in 4 directions: left, right, up, and down, using a blend tree that handles smooth directional movement. But right now, when the player stops, we don't have any idle animation in all directions. The current idle animation we have doesn't match the direction we're the player facing. In this tutorial, we're going to fix that. We'll set up a directional idle system so that when the player stops moving, they enter the right idle animation based on their last direction, whether it's up, down, or side. We're going to use a second blend tree for idling and smoothly transition between walking and idling depending on the player's input. Now, let's jump into Unity and create our directional idle animations. First, open the animation window and make sure your player character is selected. Click the Create New Clip button, and let's name this one Side Idle. Inside the Animation tab, drag the appropriate idle sprite or frames for the side-facing idle pose. Do the same process again to create Top Idle. If you're using only one side idle, we'll flip the sprite in code later. Once those idle animations are ready, we can move on to the next step, building our idle blend tree to play the correct idle animation based on the last direction the player was facing. Now let's take a look at how we updated our player movement script to support directional idle animations. Here's the original version of our script. It handled horizontal and vertical input, flipped the sprite when moving left, and passed values directly to the animator. But it didn't remember the direction our player was facing when stopping. So idle animations couldn't be direction aware. Let's fix that. We start by adding a new variable called last move direction, initialized to face down. This way, the player will default to a downward idle when the game starts. Instead of using smooth input, we use getAxisRaw. This gives us clean, snappy directional values like -1, 0, or 1. It's better for pixel art and grid movement. Next, we use last move direction to decide if the player is looking left or right. If they last moved left, we flip the sprite. Otherwise, we keep it facing right. This line ensures we only update the facing direction when the player is actually moving. That way, when they stop, we still know which way they were facing. Here, we pass the last move direction values to the animator, so it can play the correct idle animation based on the direction. And we also pass the speed, which is used to transition between movement and idle. With these changes, your character will now stop and idle in the correct direction. A key detail that brings more polish and realism to your RPG. In the next step, we'll jump into Unity's Animator and create a blend tree to make all this work visually. Alright, let's head over to the Animator tab and clean up our idle setup. First, select your Player Animator controller. And if you had a default idle animation state, go ahead and delete it. We won't be needing it anymore. Now, let's add a new parameter to drive our animation logic. Click the plus button in the Parameters panel, choose Float, and name it Speed. This will help us determine when the player is idle versus moving. With that done, let's go to the base layer and right-click in the empty space. Select Create State from New Blend Tree. Rename the new blend tree to Player Idle Tree. This is where we'll plug in our directional idle animations. Double-click to enter the blend tree and let's get started building it. Now that we've created our Player Idle Tree, let's configure it to blend between idle animations based on the direction the player is facing. Inside the blend tree, make sure to set the blend type to 2D Simple Directional. Then, assign the X input parameter to X input and the Y input parameter to Y input. These are the same parameters we're setting from our movement script. They'll help the animator know which direction to show when the player is idle. Next, click the plus button 4 times to add 4 motion fields, one for each direction, up, down, left, and right. Now, we're ready to plug in the idle animations and map them to the right directions. Now let's assign our idle animations to the motion fields we just created. Start with your idle right animation, add it to the 3rd slot and set it to X equals 1, Y equals 0. Next, assign your idle left animation to the 4th slot and set its position to X equals -1, Y equals 0. For the idle down animation, drag it into the 1st motion slot and set its position to X equals 0, Y equals 0, 1. And finally, grab your idle up animation, drop it into the 2nd motion slot and set its position to X equals 0, Y equals 1. If you're using a single side-facing animation and flipping it with code, you can assign that same clip to both left and right, and let your sprite flip handle the difference. At this point, your blend tree is ready to dynamically play the correct idle animation based on the last direction your player moved in. Now that both our idle blend tree and movement blend tree are ready, let's set up the logic that tells the animator when to switch between them. Back in the animator base layer, locate your player idle tree and your player walk tree. Right-click on Player Walk Tree and choose Make Transition. Then drag the arrow to Player Idle Tree. With the transition selected, in the inspector, uncheck Has Exit Time and add a condition, speed less than 0.01. This means if the player is not moving, we switch to idle. Now, do the reverse. Right-click on Player Idle Tree, make a transition back to Player Walk Tree. Again, uncheck Has Exit Time, and this time set the condition, speed greater than 0.01. These two transitions will handle switching between idle and movement states automatically based on how fast the player is moving. Alright, now let's hit the play button and test everything we've built. Move your player around the scene. You should see the correct walking animation play as you go up, down, left, or right. Now stop moving and watch closely. The player should automatically transition into the idle animation that matches the direction they were last facing. If you walk upward and stop, you should see the idle up animation. Walk left and stop, idle left. Everything is running through the blend tree logic we set up, driven by the speed, shinput, and yinput parameters. This small detail adds a huge amount of polish and realism to your RPG. And that's it for this part. If it worked for you, give the video a thumbs up and don't forget to subscribe for the next steps. We've got attacks, interactions, and enemy AI coming next. If you found this helpful, don't forget to hit that like button and subscribe to the channel for more Unity RPG content, animations, combat, AI, and much more coming up. Welcome back, warriors! In today's episode of our Unity 2D RPG series, we're giving our hero a weapon, and more importantly, the ability to attack in every direction. Whether you're facing up, down, or sideways, we'll set up a system to trigger the right attack animation based on your movement direction. This is a huge step toward building dynamic and responsive combat in your game. So grab your sword and let's slash some pixels. And hey, if you're enjoying this series, make sure to hit that like button and subscribe so you don't miss the next upgrades to our RPG world. Alright, let's jump into Unity and get to work on our attack animations. Open the animation window and make sure your player character is selected in the hierarchy. We're going to create 3 new animations for now. Create new clip, name the first one attack side, and save it inside your animations folder. Drag and drop the sprites for the side attack into the timeline. Adjust the keyframes to make it feel snappy and impactful. Once you're done, repeat the same process to create the attack up and attack down animations. Keep the frame rate consistent, like 12 frames per second, and make sure loop time is disabled. We only want the animation to play once per attack. Now that we have our attack animations ready, let's set up the Animator to play them based on which way the player is facing. Open the Animator window and select your player Animator controller. First, let's add a new parameter. Click the plus button in the Parameters tab, select Bool, and name it is attacking. This will control whether or not the player is currently in an attack state. Next, let's create transitions from the movement blend tree to each of these attack states. For example, right-click on your walk blend tree and choose Make Transition Attack Side. In the inspector, uncheck Has Exit Time. We want the attack to trigger immediately. Now add 2 conditions. Is attacking equal to true X input greater than 0.1 or less than negative 0.1, depending on how you handle left-right flipping. Repeat this logic for attack up with condition input greater than 0.1 and attack down with Y input less than negative 0.1. This setup ensures the correct attack animation is triggered based on the direction the player is facing when the attack input is received. Now, let's write the code that will trigger the attack animation when we click the mouse or press a key. To keep things clean and scalable, I'm moving the attack logic into a new script called playerattack.cs. This will handle all input, animation, and logic related to melee combat, while our movement script stays focused on, well, movement. It's a good habit that pays off when your project grows. Let's start by creating a new script called playerattack. This will handle our melee attack input and logic, and keep our code organized. Back in Unity, select your player and attach the player attack script to the same game object. Now drag the animator and rigid body 2D into the correct slots in the inspector. Let's make sure our attack resets after the animation finishes. Open your attack down animation in the animation window, go to the last frame, and click the Add Event button. Call the reset attack method we just created. Repeat this for all attack animations. Let's create a dedicated animation for attacking to the left. Just duplicate the side attack state, add a new transition, click on the transition arrow, and in Inspector, uncheck has exit time. Add conditions. Alright, now that we've set up the left side attack animation, let's hit play and test it out. I'll move the player to the left using the arrow keys or A key, and then click to attack. If everything works correctly, the player should play the left attack animation when facing left and return back to the movement state right after. Make sure the transition feels smooth, the animation only plays once, and your player doesn't get stuck. If your character flips correctly and the attack looks good, great job, it's working. Now don't forget to smash that like button if this helped and subscribe to stay tuned. We're going to make this RPG feel truly alive. Welcome back to the series. In this episode, we're going to add a satisfying slash effect that plays each time our player attacks. This little detail makes combat feel way more impactful, and it's super easy to set up using Unity's built-in tools and a bit of animation logic. Let's dive in. Import a slash animation into Unity. Set sprite mode to multiple and open the sprite editor to slice set filter mode to point, no filter, if you're going for a pixel style. Select the sliced sprites. Create the animation. Name it slash effect. Do the same for the slash effect, top and side. Turn it into a prefab, remove it from the scene, we'll instantiate it via code. Now let's update your player attack script so that it instantiates the correct slash effect prefab depending on the direction the player is facing. Top, side, or down. But before that, make sure that the loop time is unchecked for the 3/ animation. Alright, let's set up the player attack script, the brain behind our directional melee system. This script will handle attack input, play the correct slash animation, spawn a visual effect based on direction, and block movement while attacking. Begin by creating public references to the 3 different slash effect prefabs: side, up, and down, and an attack spawn point where we'll spawn the slash effect during combat. We also store the last move direction and grab a reference to the animator. Inside Start, we cache the animator to trigger animations efficiently later. Next, inside Update, we check if the left mouse button is clicked. If the player isn't already attacking, we set is attacking to true and call our play/effect method. Here's where the magic happens. Based on the direction our player was facing, we spawn the right/effect prefab, either above, below, or sideways. It makes the feedback feel sharp and responsive. This method allows our movement script to send us the last move direction, so the slash effect plays in the correct orientation. To make sure last move direction is updated correctly, call this in player movement script. Now, in the Inspector tab, assign /effect side, /effect up, and /effect down to the script. Create a child transform in front of the player and assign it to attack spawn point, or you can drag the player game object instead. Boom! We see the slash appear, but wait, it doesn't go away. That's a problem. It stays forever in the scene and will eventually slow down our game. Let's solve this by automatically destroying the slash effect when its animation finishes. If you don't want to use animation events, you can also destroy the object using a timer. Now let's test again. We press space, the slash appears, and it disappears. Clean, efficient, and perfect for your combat system. But you can see that there is a little problem with the animator. Let go to the animator and add some transitions from the idle tree to the player attack animation. Now let's take our slash effects to the next level. Right now, the slash appears, but no matter which direction the player is facing, it always looks the same. That's not ideal, especially when we attack to the left. So what we're going to do is flip the slash effect horizontally when the player is facing left, using the sprite renderer flip X property. Now, let's go ahead and test this in play mode. I'll press left and slash, boom, it's flipped. Press right and slash, it's normal again. Feels way better and adds polish to your combat system. And that's how you flip any visual effect using sprite renderer in Unity. Small detail, huge impact on how your game feels. Don't forget to like and subscribe if you're learning something new, and I'll see you in the next episode. Hey devs, welcome back to the series. In this video, we're going to take our attack system to the next level. It's time to improve the feel and flow of our slash animations. If you've been following the previous episodes, you already have directional slashes and attack triggers set up. But today, we're going to add polish, smoother transitions, animation timing, maybe even hit pauses or follow through. Let's start this episode with something super important. Disabling the player's movement while they attack. We don't want the player to run around while swinging their sword. It breaks the realism and makes the combat feel floaty. To do that, we're going to temporarily disable our player movement script during the attack animation and then re-enable it afterward. Inside our player attack script, let's create a coroutine that disables movement, waits for a few seconds, and then turns it back on. Let's test it now. When we attack, our movement freezes briefly and resumes right after the animation ends. Simple, but it makes the slash feel so much more grounded. If this helped improve your own system, don't forget to smash like, and let's keep refining this RPG together. Now that movement is locked during the attack, let's tackle the next detail. Adjusting the position of the slash effect. We want the effect to appear exactly where it makes sense, above or below the player, depending on the attack direction. To keep things clean and flexible, we're going to create two empty game objects inside our player. One for top slash spawn and another for down slash spawn. These will be used as spawn points for the slash effects. This way, we can easily control where each slash effect appears without touching the code or hard coding positions. Now that we've created our top/spawn and down/spawn points inside Unity, it's time to plug them into the code. Inside our player attack script, we'll start by creating 2 transform references, one for the top effect spawn and one for the down effect spawn. These will hold the position where we want to spawn each effect. Then, when we perform an attack, we'll check the direction and instantiate the correct /prefab at the correct spawn point. Don't forget to assign the top/spawn and down/spawn in the Unity inspector. Just drag your empty game objects into the fields. Let's hit play and test it. Our slashes now appear in the right place with 0 hard-coded positions. You can add the left and right slashes. The process is exactly the same as we did for top and down. In this episode, we're giving our enemies some brains and some style. We'll add smart behavior so they can chase the player, stop at attack range, and use proper animated movement in all directions. Let's build a clean and expandable enemy AI system using state logic and blend it with 2D directional animations just like we did for our player. Let's bring our enemy to life. We're starting with the very first animation, the enemy idle animation. This is the state your enemy will be in when not chasing or attacking, just standing and waiting. With the enemy selected, open the animation window. Click Create and name the animation Torch Enemy Idle Drag. The idle frames from the project window into the animation timeline. Adjust the sample rate if needed for smoothness. In the inspector, make sure loop time is enabled for the animation. This way, the idle animation will play continuously. Now hit play and watch your goblin breathe and twitch with idle menace. That's it for the idle animation. In the next steps, we'll add chasing and attacking animations and connect them in the Animator to build our enemy's behavior logic. Let's now write the brain of our enemy, the script that makes it idle by default, and then chase the player when they get close enough. We'll call it Enemy AI Script, and we'll use basic distance checking to control enemy behavior. We'll expose detection range and speed to control how the enemy reacts. Then we grab references to the player, rigid body 2D and Animator, plus a movement vector. Inside Start method, we find the player using its tag and grab our rigid body 2D and Animator. Make sure your player is tagged as Player in the Unity inspector. We measure the distance between the enemy and the player. If the player is within range, the enemy calculates the direction to the player and starts moving. We also update the Animator parameters. This is key for making the enemy blend into walk or idle animations smoothly. If the player is too far, the enemy stops and the animation switches to idle. In Fixed Update, we actually apply the movement to the rigid body. This keeps it smooth and physics-friendly. Notice we're using move position instead of setting velocity directly, which is better for top-down games. Now inside Unity, assign the tag player to your player game object and attach this script to your enemy game object. Add rigid body 2D, body type equals kinematic, and a box collider 2D. Right-click in the Animator canvas, Create State from New Blend Tree. Go to the Parameters tab, add 3 new parameters: X input, Y input, and speed. In the inspector, change Blend Type to 2D, Simple Directional. Parameters: X input and Y input. Make sure on the code we are looking for the player tag. Alright, let's test if our enemy AI is actually detecting the player as expected. Now, when the player enters the detection zone, we should see the enemy start chasing. And the directional movement animation should kick in through our blend tree. Welcome back, friends! In this part of our 2D RPG series, we're going to keep working on our enemy AI to make the gameplay even more dynamic and engaging. Last time, we set up basic detection and movement. Now it's time to level things up. We'll refine how the enemy behaves, add smarter reactions, and prepare the foundation for future combat logic. Whether it's chasing, idling, or attacking, your enemies are about to feel much more alive. Now, let's add some visual feedback by making the enemy face the player. We start by getting a reference to the sprite renderer component, and then we check the direction of movement on the x-axis. If the enemy is moving left, we flip the sprite. If it's moving right, we keep it normal. This makes the enemy look a lot more dynamic and visually responsive. Now, as in the enemy AI script, let's add a sprite renderer and flip it based on player direction. Let's test it. Now our enemy turns toward the player when chasing. That's a small change with a big impact. Now we're giving our enemy some brains before the chase. It'll patrol between 2 points until it sees the player, at which point it switches to chase mode. This adds realism and life to the game world, even before combat starts. Simple logic, but super effective for RPG or stealth mechanics. In Unity, create 2 empty game objects. Name them Patrol Point A and Patrol Point B. Position them where you want the enemy to patrol. Now, let's open our enemy AI script. We'll start by adding references to the player and our patrol points. We'll use current target to tell the enemy where to go, either A or B. and a boolean to check if the player is within range. We also grab a reference to the sprite renderer so we can flip the sprite during movement. At the start of the game, we want our enemy to head toward point B. We also cache the sprite renderer component for flipping. This chunk handles switching between patrol and chase logic. We check the player's distance, and if they're close, we start chasing. Otherwise, we patrol normally. In the patrol method, the enemy moves toward the current target. Once it's close enough, we flip the target, creating a simple back and forth patrol. Finally, our move towards method handles the actual movement and sprite direction. If the enemy is walking left, we flip the sprite. If right, we reset it. Let's hit play and watch our enemy patrol calmly between 2 points. Now, if we approach with the player, boom, the enemy switches to chase mode instantly. It's a simple patrol mechanic, but it adds so much realism to our game. Now we're going to make our enemy smarter. Instead of turning instantly at each point, they'll wait for a moment before continuing their patrol. This small delay gives the enemy a more lifelike patrol behavior. Let's open enemy script and add 2 new variables, one for the wait time and another as a countdown timer. Inside our patrol method, we'll pause the enemy when it reaches a patrol point by using the IS waiting flag. We've now connected our enemy's movement to the animation blend tree. This means the sprite will animate and turn in the correct direction, whether patrolling or chasing the player. We're using setFloat to update X input, Y input, and speed. just like we did with our player character. This keeps both player and enemy systems consistent and smooth. We added a timer and a simple check. If the enemy reaches the point, we pause the movement and wait for the countdown to finish before switching to the next patrol target. Let's hit play. And perfect. The enemy walks, pauses, then continues. This tiny detail makes a huge difference in game feel. Now that our enemies can chase the player, it's time to teach them how to fight back. In this episode, we'll give them a proper attack, complete with animation, range detection, and damage to the player. Let's dive in. Now it's time to bring our enemy to life with proper attack animations. We have 3 animations, one for attacking up, one for down, and one for the side. Let's hook them up inside the animator and set the transitions based on direction. In the Animator Parameters tab, add a new parameter is attacking of type Boolean. Let's make our enemy switch from movement to the correct attack animation based on direction. From the movement, blend tree, right-click, make transition, attack up, select the transition arrow, uncheck, has exit time and add conditions. Is attacking equal to true and Y input greater than 0.5. Repeat for attack down and attack side. Now we need to return to our movement. Blend tree once the attack animation is finished. For each attack state, attack up, attack down, attack side. Right-click, make transition, back to blend tree. Select the arrow, has exit time, checked. Now that we've set up our attack animations based on direction, it's time to write the logic behind them. We're going to create a new script called enemy attack that will detect when the player is close enough to attack, play the appropriate animation, and later, deal damage. Inside the update method, we're checking if the player is within our defined attack range. If they are, and our cooldown is ready, we calculate the direction to the player and set the animator's X input and Y input so we can play the right directional animation. Then we trigger the attack parameter and reset the cooldown timer so the enemy doesn't spam attacks every frame. Now let's hit the play button. As soon as our player steps into the enemy's attack range, the AI will stop moving and trigger the appropriate attack animation, striking the player based on their position. Just like that, our enemy is now fully capable of detecting, stopping, and attacking in real time. In the next episode, we'll add a health and damage system to our player, making every enemy hit count. If you're enjoying this series and want to keep leveling up with me, don't forget to drop a like, subscribe, and hit the bell so you don't miss what's coming next. In this part of our RPG series, we're going to give our player a health system. So taking damage finally means something. Let's start by creating a new script called Player Health. This script will handle how much health the player has, how to take damage, and what happens when that health hits 0. Later, we'll connect it to our enemy attacks and even add a death animation and game over logic. For now, let's jump into the code and build the foundation of our health system. Let's start by creating a public class called Player Health, which inherits from mono behavior, so we can attach it to our player game object. We define a max health value that represents the player's full HP and a private variable to keep track of the current health. Inside start method, we initialize the player's health. Now we write a public method called take damage. This will reduce the player's current health by the amount passed in and log it to the console. If we have an animator, we trigger a hurt animation. This is optional, but adds a lot of polish to your game. Then we check if health has dropped to 0 or below. If so, we call a method called die. Inside the die function, we log that the player has died and trigger the die animation if we have one. We then disable the player movement script to stop the player from moving, and finally disable the health script itself to prevent any more updates. And that's it. We now have a working player health system ready to be connected to enemy attacks. Let's now update our enemy attack script so the enemy can actually damage the player during an attack. First, we add a private player health variable to hold a reference to the player's health system. Inside the start method, we grab the player health component from the player game object. Next, we move into the update method. We now make sure the player and player health references are both valid before running any logic. If the player is in attack range and the enemy is not on cooldown, we calculate the direction, set the animation, freeze the enemy, and most importantly, we call take damage method on the player to apply actual damage. This makes our combat finally meaningful. We reset the cooldown, and when out of range or cooling down, we reset the animation and free the rigid body constraints to allow movement again. Now that we've finished scripting our player's health system, let's switch back to Unity and apply the script to our player game object. First, click on the player in the hierarchy. Then, in the inspector panel, click Add Component and search for Player Health.